Hello, welcome to an introduction to some infrared spectroscopy concepts. I noticed that I pause in kind of an odd way, and I think part of that is because I like having a conversation more than just talking and feeling like it's for an audience only. I know that I'm hoping to get more videos out before I tell anyone about them, so I will probably pretend there's somebody around that might answer back to me, even if that sounds like I'm talking to myself. It might make this flow a little better. If anyone does happen to pop into the live chat, feel free to comment. And of course, questions are wonderful. If you write question if you want me to respond, it's likelier that I'll see it. I'm pretty new at this, so we'll see how that goes. For this particular one, I do plan to use slides again and just give kind of a little bit of an overview of a couple things and also a couple of details on other things. So that's very vague, but I put in the description that I'm going to be talking about infrared spectroscopy, specifically Fourier transform infrared spectroscopy that I've actually done. And also how to find a lot of public information, spectra, based on a wonderful database library where a bunch of people have input all kinds of information into it. And so a lot of people have taken data and put it into easily searchable ways to get it back and totally free database. So let me share slides. And describe what I'm talking about here. So, oscillators and rotors are the concepts that a lot of infrared spectroscopy is based on. And I'm going to come back on screen and do a little bit of a molecule dance in a minute because while I'm not going to get into it too deeply today, it does help to visualize what's happening in infrared spectroscopy. So first of all, let's talk about what we can get from infrared. One of the things that is really useful that you can often get from simple molecules is information about how strongly bound two atoms are to each other. And if you get that, that gives you a lot of information about atom to atom linkages and how hard they are to rip apart compared to other atom to atom linkages. So if you think about ripping apart a carbon and a hydrogen bond versus an oxygen and a hydrogen bond, it's really useful to know which of them is more difficult to do, which one takes more energy or more, put it another way, more heat or stronger light or higher energy light. So if you have ideas about things that you would like to know what infrared could do, I would love it if anyone watching this later comments. Another idea from me about what infrared can do is help to identify unknown molecules. And this one usually, in my experience, infrared is a wonderful tool for molecule identification with other techniques. A classic thing to do is to take certain types of organic molecules and take an infrared and an NMR spectrum of them and then put together the information to figure out what kind of molecule it is. A lot of other techniques can help. In a lot of cases, just figuring out what melting points are and all kinds of things that are unique fairly unique to molecules can help to determine what an unknown might be. There's a whole bunch of people who work on figuring out unknown molecules. And infrared is one of the tools that is used for certain types, typically of organics. And we could talk about more about that if people request it, or if I decide I'd like to just do it. So that might be the topic of another video. So I'll probably come back on camera after this slide and talk a little bit about some of the movements that the oscillators and the rotors do that help them to absorb infrared. First of all, though, I just want to place infrared into kind of the context of a lot of the different radiation types that there are. And this slide is a little busy, but the idea here is that for the electromagnetic spectrum, I've listed different types of the spectrum. A lot of people are familiar with these, and shown that increasing wavelength is actually going to be in the direction of decreasing energy. So I think it might be somewhat intuitive that X-rays are very high energy and radio waves are very low energy. What not everybody might know is that X-rays are very, very short in wavelength, and radio waves are very, very long in wavelength. I mean, the height of a person is part of what would be the distance from peak to peak of a radio wave. And it's a long band too, so radio waves could be shorter than a person or longer than a person from peak to peak. Infrared is less energetic than the visible spectrum, and it's beyond the visible red in terms of being less energetic, and that means that the wavelengths from is longer than the visible. So it's actually a pretty wide band as well compared to visible, and so a lot of the infrared that people talk about, it depends on what they're doing with it. Some people talk about near infrared, which is closer to visible red, and some people talk about far infrared, which is less energetic and further away from visible red, and some people talk about mid-infrared between those two. So um, that's just some of the terminology you might encounter when you're talking about infrared. I don't plan to do the problems this time as I go through, but if I get better about using a whiteboard as we go, I definitely do plan to do them. So again, I'm coming back on screen for a minute. I'd like to show a little bit of a molecule dance so that we get a context for what I'm talking about. So infrared energy is lower energy than visible, so the things that tend to interact with it, interestingly, are the vibrations within molecules. So the two atoms, say, would have always motion between them. So the molecule, say that I have a hydrogen atom and a hydrogen atom, and they are connected together. So it's an H2 molecule. And they are not going to be still in space. They'll always be moving while they're linked together. This is called translational motion as they move around. Even if they're not going to, if you're not focusing on the translational motion, we can focus on their internal motion. So if it were just one atom, what it has is translational motion. It's going around. If we have two atoms, we can talk about the internal motion between the two, the relative distance between these two atoms. So this is also never still. And so the vibration between two atoms can be actually different speeds and have different frequencies. So if a molecule with hydrogen goes from a speed like this to a speed like this, those are two different frequencies. Oh, my camera's not good enough to pick that up. Hydrogen molecule would not interact in a determinable way with infrared because there is no dipole moment, which means that the positive and negative forces between them are even, and there's no, say, negative or positive side. But that's different if you have a carbon and an oxygen, and you have a carbon monoxide molecule. So let's say that the oxygen is my hand with the watch, and the carbon is my other hand. These two are going to be vibrating as well, and if the energy change between these ones leads to an increase in the speed of this vibration, it needs some kind of energy gain to go from slower to faster like that. And conversely, if we go from this speed to even slower, oh man, I'm making that uneven. this would mean that the molecule had lost some energy. Just like if you're talking about translational motion, this molecule going in space at a slow speed like this would take less energy than zipping around at a fast speed like this. So internally, there's similar concepts. If you're going at this frequency and then you drop down to this frequency, the molecule has lost some energy to do that. And that is detectable in infrared. That energy loss would be able to be seen. And if you're doing infrared spectroscopy, you can shine infrared light at molecules and see that some of the energy will be absorbed into the molecule to increase the frequency of vibration. That's the kind of motion that is interacting with the infrared, is those energy changes in vibration. Another one that shows up, since infrared is such a strong band, is the rotor type of thing. And I'm not going to talk much about this today, but I will touch on it briefly. So vibration is happening internally within molecules with multiple atoms, and rotation is happening. So the molecules can turn relative to each other, make circles, and there could be more complicated molecules, but whatever it is, they don't have to stay in the same plane. They can rotate. So that is a rotor idea, and that also can be detected in infrared spectroscopy. It takes transition from faster to even slower rotations would be a change in energy needed to do that, and that would be an energy difference that you could actually see in infrared spectroscopy. The idea in spectroscopy is, in a nutshell, a lot of times that you're shining some kind of light on a molecule, many times, and then you're going to have a detector that detects what light reaches the detector after it hits the molecule. So if the molecule absorbs some of the light to go from slower vibration to faster vibration, that light no longer is going to be detected by the detector. And so you will know that some molecule removed it, and you know the frequency that got removed, and you can start determining things about the molecule. Because a carbon and a oxygen molecule will have certain bands that they will go through as they do this. They do not just go continuously through all of the wavelengths. And I will definitely love to explain that in a different video, but that is another subject, related, of course. And they are specific, though. It doesn't just go at every single speed. It'll go jump to certain specific speeds. It's not like an analog dial where it's just going up through the entire light range. So it'll go from certain specified speed and then not just any old speed, but a certain other specified speed and in a certain other specified speed. And so very specific infrared bands will come out of that molecule as that energy gets absorbed. Back to the slides. This is an example of using a library to get a spectra, and I pulled it already, but I have given the NIST chemistry web book address, the web address at the bottom of the slide. Might be a good idea for me to link that to the chat below, or to the comments below. So I will try to remember to post this, because this is a wonderful reference. Anyone can use it, and you can go through and look up molecules and their spectra online. And so I just pulled this. I'll give an example of doing that soon. And what you see here is that this is for water, and it's a liquid water, not steam, not gas. And transmittance here means that at the bottom we have 0 transmittance. So that means that everything did not reach the detector, and if we had 1 transmittance, that meant everything did reach the detector. So if nothing reached the detector in this energy range. And by the way, wave numbers are a measure of the wavelength, but inverted. That means that this area in the 3000 something wave number range was absorbed. So water was able to use this for a transition in vibration. And then there's another pretty sharp one, right around 1600 wave numbers. And wave numbers are inverted. I mentioned that the longer a wavelength is, the less energy. And this is flipped so that, but also the axis is backwards. So everything is fun about spectroscopists. You can sometimes do this yourself to replot the data. But anyway, this is higher energy that it took out of the spectrum than this is. This is 3000 something. It looks maybe like around 3600. This is around 1600. And so for water, I can talk about what that looks like, actually. I'm not going to get through all these slides today. I'll do a part 2 because I'm having a lot of fun doing the molecule dance, and I don't want to spend too long today on this particular video. So this is the start, and I'll do a part 2 later. But if my head is the oxygen of water, which is H2O, and my hands are the hydrogens, you can imagine that there are different ways for vibrations to happen. And one of them would be, and I have to mention, water wouldn't just be flat, straight side to side from my head. It will be at an angle from my head. And it is hard to see on video. It's a lot easier to see in real life. But I can see kind of that I'm holding my hands out in front of me, just like the hydrogens would be. They wouldn't be on either side, opposite from each other. They'd be at an angle. And that's because oxygen has other electrons that help push the hydrogens off to these angles. And so one of the vibrations would be that the oxygen moves back and the hydrogen moves forwards. Another one could be that one hydrogen is moving away from the oxygen and the other one's moving closer and the oxygen moving closer to it. So this would be another way it could be vibrating. Another one could be that the oxygen is slightly moving closer and the hydrogens are moving closer together. So this is more, you can see almost like a scissor motion on the hydrogen's part, and the oxygen isn't doing much, but it's slightly bending in. The center of mass here is not changing. Of course, I'm not doing it perfectly, but the idea is that this molecule, we're focusing on the abbreviation, even though water, of course, is moving all over the place as a whole molecule, but it's also internally moving, and that's what we're focusing on. So the vibration where the hydrogens are moving like this out and in from the, away from and towards the oxygen, even this one where they're both doing that, but at different, that one's in and one's out. Let's see. The oxygen should move towards the hydrogen that's moving towards it. So can I get that right? Yeah, kind of. That one is the higher energy set of transitions, where changing speed on this takes a lot of energy. So that transition is in the 35, 3600, 3700 regime. And it's different, if it's even or if it's uneven. So we couldn't tell the difference. They were smeared together. But this one, this bend, or what is this one called? I'm going to look it up again. I used to know, and I expected to remember, but I tend to forget things when I'm on video. This motion, if speeding it up doesn't take as much energy to change it. So this is, the initial change was around 1600 to go from slower to faster. Back to the slides. I think that I will skip over atomic layer deposition today and probably have to edit the title. But I want to give an example of a gas spectrum. This is infrared. And of course, I need to mention that water has a lot of different environments that each molecule is in, depending on how close it is to other molecules. And gas tends to have a lot sharper transitions because each molecule tends to be further away from every other molecule and be, on average, about the same for each transition. So if you have a bunch of waters clustered together but all different distances from each other, you affect how easily it is for vibration to happen, how much energy the change will be. So you have this energy range going on for each molecule that's in a different distance to the other waters. But for gas spectra, and here we have isopropanol or rubbing alcohol, these transitions do look sharper. And this is a molecule I should have written down the formula for. I can say it out loud at least. Isopropanol is a carbon with 3 hydrogens on it, and the carbon is attached to another carbon as well as the 3 hydrogens. And that carbon has an oxygen hydrogen off it, and another carbon with 3 hydrogens off it. So that would be something that would be good to include a 3D model of if I remember to link that. And so there's a lot of vibrations going on here. You can see all kinds of peaks, and they're not as spread out and blobby. If we go on to just one more thing I want to mention on a side note way is that people who are struggling with the idea of spring energies and springs in general and want to go here, there's a wonderful website that I'm giving the address of here in a rather a weird way. Again, maybe I'll remember to put this in the comments. That allows you to enter values for springs, like how heavy they are and whatnot, and see how that changes how the spring moves. It's a nice visualization of it. I much prefer pictures and videos than just words. And I'm going to skip past this for now and get back to it. But I just want to point out that we initially looked at liquid water, and if water is in the gas phase, then the spectrum here looks insane compared to that if you don't understand where all of these tiny little peaks are coming from. And that goes into not only is this molecule vibrating, but this molecule is also rotating, and those rotation speed changes are visible in a gas spectrum in the infrared. So a lot of these peaks are different speeds of rotations along with changes in speed of vibration. And this is a lot of information you can get out of a gas spectrum of an H2O molecule. All right, so again, I think I'm going to go ahead and pause there and make a part 2. I will remove ALD from this title and go into it in more detail next time, along with how continuing on to find that dissociation energy that I mentioned initially. It's a really fun problem to do, and now that I've introduced infrared, I think I'll do the find the dissociation energy as a part 2. I hope that that made in some sense to somebody. I really do enjoy talking about it. I love doing infrared spectra. So sometimes I do forget what people would tend to know, and I don't know who my audience will tend to be, but I will try to get better as I go about introducing things from the ground up and giving references if I jump off into a little bit too technical. A lot of the technical parts are intended to be as you wish. If you're interested, dig deeper, and I'll try to give lots of explanation for the how would you conceptualize this. I will plan to do a part 2, and for now, thank you to anyone who watches this.